Hi, am I audible? Can anyone please respond to so that I'm audible
Yeah,
or not?
yeah,
Yes,
yeah,
sir.
yeah, yeah.
Okay, so today I will be giving a talk on random signs. It's a basic principle, so let's get started. Don't think. Yeah. Is the screen visible for everyone or?
Yes,
Yeah, so I'm Subhojit and I will be giving today's talk on random signs. So basically this obviously random science is not the actual lemma. It's a lemma from Littlewood and Offord. So there are four sections of this talk. The first will be the introduction to the problem. The second will be how we go from a small level set to a higher dimensions, and then we'll do the proofs and then some takeaways from that. So the first thing is we start with a game. So you want to choose some numbers, some non-zero real numbers that are greater than one, right? And for each one, you decide to use it with a plus or minus sign, like you sum it up or you take the difference. So each of these signs that are there, the plus and minus in each of these are determined randomly. So it's either a plus or a minus. So there are total of two to the power n configurations if you think about it, because each of this plus and minus have two possibilities, and then there are n plus and minus signs. So our question is to ask, if we start with something that is initially greater than or equal to 1, that is initially it has a huge size, can we land on can this sum, or what is the probability that this sum lands on something that is very small, or that can be bounded in a particular region or something, small region. So a little bit of warm up. If we take all of them to be equal, that is A1 is equals to A2, that is equals to A3, and that is equals to A4, and all of them 1. So then every signed sum of this is basically 0, 1, 2, 3, 4, if you think about it. And like the number of plus and minus signs, and then the sum would be -4, -2, 0, 2, and 4, depending on the choices. Now, for each plus signs that you take, there are a number of choices for where you can put the plus signs. So, for the example of let's take two plus signs, then it can be here and here, or it can be here and here, or it can be here or here. And the same way for the other there are six number of cases. That is 4 choose 2, right? Simple combinatorics if you can get it. So, so the middle value occurs 4 choose 2, that is equals to 6. Now, there's a trace back. What if I had not given you that they were positive? I just told you that the mod value was greater than or equal to 1. Anyone can they answer if what would happen if I had taken mod of A1, mod of A2, and like that mod of AN to be greater than or equal to 1, not just A1, A2, AN? Any ideas? Any vague ideas is good enough. I don't want the actual answer, but yeah. Anyone?
So the only absolute part would be taken of the number.
The only absolute, I couldn't get it. Could you elaborate a bit more? Hello, am I audible?
yes, sir.
Okay. The thing is, even if I take mod values for them, like mod of A1, mod of A2, or mod of AN, if I had used modulo, the sum would be the same even after that, because the possible summations that we take, because we are taking the all possible configurations of plus and minus. So let possibly that AI, some AI is negative, then we can take the configuration that is minus of that, and then we can get the configurations to it. That is the plus and minus, and then minus of AI. So it possibly doesn't change anything, even if we had a modulo operator for each one of them. So this is the basic setting that we will follow. And now moving on to something that is a bit rigorous. This was very like vague. So yeah. So Littlewood and Offord in 1943 tried to determine this question, like try to find out what would be the answer to this question. So let A1, A2, AN be some complex numbers with so complex numbers are something that you can imagine as vectors or something. So some points in the R2 plane, right? You can if you don't know, like I think there are some audience from the class 10th also. So uh, they have this modulo. The modulo in complex numbers is defined by. Wait a minute. Uh, just how should I escape this? Yeah. So the modulo is defined as x squared plus y squared to the power half. That is there for. I think this should be known to all, but still, just for the sake of completeness. So this is what the modulo operator does. It takes the root mod by the absolute value or the distance from that distance of that point from the origin. Right. Okay. So now they asked how many of these sums would lie inside a circle of radius 1. That is the question. That what is the probability that you get this sum to be within a circle of radius 1, or that is to be a bit exact, that is a mod of z should be let us determine this sum to be z, the value of the sum, then mod of z should be, yeah, what is meant by the sum inside the radius? Okay, so the sum inside this radius 1 is basically, if you think about it, wait a minute, again I should just a minute. So this sum is basically S. Let this sum be denoted by S, the random sum that is there. So for each one of them, you determine if it is a plus or minus randomly. Let's say with probability half and half, so that it is uniform. Now you have a circle on this complex plane, and then you want to find if this point S that is there, that is inside the circle or that is outside the circle of radius 1 from the origin. Am I clear? Who asked the question? I don't know. Kamlesh. Okay. Yes. So that is it. Yeah, the origin of the circle is the center. Center of the like 0, comma 0. The origin. Now, the condition that is mod of AI to be greater than 1 says that each vector that is there, that is a complex vector, or the R, even in R2, it is a vector that has a magnitude that is greater than the radius. So it always has a tendency to go out of the circle if you think about it. So this question seems interesting because of this condition of mod of AI being greater than or equal to 1. So I start with something that is always tending to go out of the circle, but somehow I end up being in the circle. So the problem basically asks how much crowding is possible or within the circle or that is there. So to answer this, Littlewood and Offord gave a very good optimal bound for the probabilities, but then there came Ardosh, and then he said some really nice stuff. So we'll focus on Ardash's proof and how he went on to do it. So Ardash's answer for the real number case. So now moving from the C complex numbers, we go to real numbers. And real numbers, if I have something as AI being mod of AI being greater than or equal to 1, the maximum number of sums that can happen in an interval of length 2 is exactly n by, sorry, n choose n by 2. That is the greatest binomial term from n of n choose k, of the form n choose k. So why is it exactly this? So what Ardhash did is he formulated this question back to real numbers. So how does this question formulate back to real numbers? A1 to AN are all reals, obviously. AI is greater, mod of AI is greater than 1. And then he asks how many of these sums can lie inside an interval of radius 2, not a circle of radius 2, because you won't get a circle in complex numbers. Sorry, in real numbers. You won't get a circle in a real line, right? So he asked about what is the probability that it lies in an interval of 2. So now he said that the maximum number of sums that can lie in an open interval. So an open interval is something that is of this form that I can show you. I think you should know this. Something of the form A to B, not including A and B on the edges, obviously. Yeah, that is. Now, so why is this so a vague approximation to this is, if we had taken that the all of them to be equal, then the middle value that occurs, as you have seen right here, the middle value that occurs, that is plus signs being 2 and the number of minus signs being 2, is basically 6 times, or that is 4 choose 2, or to be a bit more general, n choose n by 2. So that comes back to here. That is the middle value occurs and choose n by 2 times. And now by Stirling's approximation, we have that it is 2 to the power n by root n. So you can do the Stirling approximation and look at it. It's a really nice approximation that is generally used in, like, widely used in mathematics. So the proof. Now we go on to the proof. Observe that first of all, this set I, that is the number of that determines the positions I, such that the sign of AI is positive. That is, if I have been given this kind of configuration of this form, that is, let's say A1 minus A2 plus A3, or some way or the other, the plus and minus signs are arranged. So this set I, that counts the positions, that indexes the positions where the plus signs occur, will give you the exact configuration, because the positions of I complement, that is, if I take the I complement set for all those positions that are not included in I, then that will have a minus sign, and the positions that are there in I will have a plus sign. Am I like clear to everyone?
Yes, sir.
Okay. So the first point is that if I have two index sets that are there, let's say, so I is an index set, obviously, indexing set. So if I have two index set I and I dash, and let's say that one contains the other, that is I dash contains I, then the sum of I dash is at least 2 larger than the sum for I. That is, as this index set I determines the summation, so I now say that the summation using this index that is obtained, and the summation that is obtained using this I dash index has a difference of 2, and the summation of I dash index is greater than or equal to this by 2. So the proof is very easy. So you have this epsilon i's to be so the epsilon i's are the plus and minus ones that are there, right? The points where the difference occurs, that is, the points where they don't match, are the only ones that are to be considered as considered here. So that is equal to 2 times of the summation of ai's for over the index set, that is I dash minus I, the signs where they don't match up. So that is greater than or equal to 2. Obviously, because ai is greater than or equal to 1, and I have that this is greater than or equal to 2. Is it clear? I hope so. Anyone? Any doubts? Okay, moving on. Therefore, two comparables. Okay, what is the epsilon here? Okay, so the epsilon here that you see is the signs that you get. That is either it is a plus one or it is a minus one. Is it clear now? So epsilon i's are, yeah. Okay. So therefore, two comparable sets cannot have open interval of length two. What we get, right? Because the set, if one contains the other, the sum differs by two at like more than two, right? So the two comparable sets cannot lie in the same open interval of length two. So the successful sets that form a family in which no sets contain the other. So this kind of sets are called the antigens. Such a family of sets in which no two elements can be compared, or that is, here compared means that two sets can be one set contains the other. The comparison is containment, right?
Sir,
Two elements can be compared. Yeah.
when did we define S of I or anything like that?
So S of I is basically the sum of the sum. So the I that you get here, that is the index set for the plus signs. Am I clear? Or
Yes, so S of I is what?
S of I is the summation that you get from the index set. So index set. So think of it like this: if the index set I contains the points 1, 2, and 4, and you have this n that is given, this n a1 to an, that is, let's say, a1, a2, a4, that is n equal to 4, and
Yes.
given that the set I is 1 to 4, and then you will get that a1 has a positive sign, a2 has a positive sign, a3 should have a negative sign, and a4 will have a positive sign.
Yes.
So that will give me a summation, right? That will give me a value.
SI complement is just negative of it.
Yeah, what?
So SI complement will be just negative of it.
Yeah, the SI complement, not the negative of it. The SI complement will be the ones that has the negative signs.
So like it will reverse
SI,
the sign.
SI complement, SI complement. No, there is nothing as SI complement. SI is the summation. It's not a set. SI is not a set. It's a sum value that you get.
Yeah, so there we had SI minus SI complement, right?
No, that's not SI complement. That is another index set I dash, not
Oh, oh,
complement I dash.
okay.
So yeah, that is another index set I dash. So I assume that I dash contains I. So there is some bigger index set that is containing this one.
Okay, got it.
Okay. So the successful events form an anti-chain. That is what we found. That is one within the interval of two. We can't find two index sets such that one contains the other. So now there's a theorem that is named as Sperner's theorem. So Sperner's theorem is widely used in theoretical computer science if you look at it. But yeah. Okay, so the theorem says that the largest possible anti-chain of subsets of 1 to n has the size n choose n over 2. The proof of this has like there are lot number of proofs for this. All of them are equally beautiful and equally elegant. But the one that I really like is the LYM inequality proof. So you can give it a read. So this is an exercise for you all. You should give it a read for the Sperner's theorem. Or if you know, that's very fantastic for the topic. So I will be assuming the Sperner's theorem. I will be not proving it right now. It takes a bit of time. So yeah. So now can you say again about antichain a bit? Okay. Yeah. So antichains are something that So you first define something as a comparison between two sets, yeah, two sets, and you have a family of sets, and you defined the comparison between two sets. Here we have been comparing using the containment thing. That is, I contains I dash. This is what how we compare, right? So if elements of the family, that is the two sets, any two sets of that family cannot be compared, or that is you can't get two sets within the family such that one contains the other here, we call it an anti-chain. Am I clear, or is there any other doubts? Okay. Okay. So the theorem of Swerner's is done now. Since the successful number of successful configurations form an anti-chain, that is within the interval of length 2, the sets form the anti-chain, the index sets form an anti-chain. The number of configurations lying in an interval of length 2 is at most this form, that is n choose n over 2. And now again, by Stirling's approximation, this was given to be big O of 2 to the power n by root n. So big O is something I think everyone should know. Is there someone who doesn't know big O of n? Awesome. The big O notation and the small O notation? Okay. So now, therefore, what do we get as a maximum probability of this? So the maximum probability over all those intervals are of length 2, that is there, you get that it is less than or equal to 1 by 2 to the power n times n choose n over 2. And in the big O notation, it is 1 by root over of n, right? So the maximum probability that you get of those summations to be within an interval of length 2 is big O of 1 over root n, right? Now moving on. So this is what Ardosh proved. Ardosh proved. Now what changes in now moving back to again from Ardosh to this problem, that is of Littlewood and Offord. So is the screen visible or is it black? Okay. Is it visible?
Yes, now is good.
Okay. Okay. So now moving back to again Littlewood and Offord. So we've Ardosh showed that it is good enough for if we take it to be real line, if the numbers are on a real line, right? We wanted to show it for complex, and then there came Kleitman. Kleitman showed it for d-dimensional vector spaces, or in general a Hilbert space, right? Where you can define a Hilbert space is nothing but something where you can define the dot product, if you know, which is called as the inner product space, something like that. For the college students, if they are here, so it's called the inner product space. If you can define an inner product in a vector space, then it is a Hilbert space. Or for the junior high school students, the vector space where you can define a dot product. It's not very possible that you define a dot product. So that is a Hilbert space. So we'll be defining it for Hilbert spaces now. So what happened in a line that was there is, that is a line has a order. If you see, the line has a order. So you go from left to right and you increase in quantity, but you can't do the same for the vectors, right? You can't say that 0 comma 0 has, sorry, 1 comma 0 has a lesser magnitude than 0 comma half, because it is on the left right hand side of 1 comma 0, sorry, whatever, other way around. So you can't say say something of a natural order in a vector space. So what do we do is, I think I have, okay, yeah. So there is no left to right order that you get in RD. R to the power D is something I think you know. Yeah. So basic notions to get started. A vector is an arrow That's what we need now. We don't need anything more than this. The norm of a vector, that is defined by a norm of ai. So this is the norm. So this defines the length of the arrow, which for which complex numbers I said that the mod value of x plus iota y is basically root over of x square plus y square to the root over. And then this similarly we define the Euclidean norm for the length of the vectors. And now for the diameter of a region. Now in a complex plane you had to define a circle of radius. You could define a circle of radius 1, right? But what happened if you didn't have a wait, what would happen if you didn't have something of a circle in d-dimensional, or let's say in dimension 3, R3, take d to be 3, you don't have a circle there to be covering all the points. You have a sphere there to be covering a similar number of points. So we define the term called diameter there. But the diameter is that you define a region such that every 2 points of it are closer than 2. The college student should take it as something supremum of x and y being within that region, mod of this. So this is the diameter function, how you define it. Yeah. Is it clear, or any more justifications that I should give to anyone? Okay. Okay. So now Arthos is conjecture. So Arthos, after giving the proof for the real numbers, he conjectured on the d-dimensional real vector space. That is, he said that let a1 to an be in R power d, and let the norm of this ai's be greater than or equal to 1. And then an open ball. Now an open ball is something which has okay, there are a lot of things which I think the students would not know. So an open ball is something, let's say you have a point x and you have to define a ball around this point, right? You have to define a ball around this point of radius r. Now the radius of this r, how will the distance of it determined? So you have an x and you take the difference from the point y, or vector y, and this defines the length of this vector from here to here. Now I want this to be less than or equal to r, and all those points y that satisfy this relation is my ball of radius r. This is my ball of radius r. Now why is it open or why is it closed is something not to be understood by high school students, but yeah, you can think of it as an open interval or something like that. Okay. So an open ball of radius 1 should contain at most this many points, that is n choose n over 2 of the signed summations, that is it. Now, Bateman showed a much stronger statement to this. Bateman showed that if I have these points in R power d, that is a d-dimensional real vector space, and I have been given that the length of each of these vectors that is there is greater than 1, and I have k many open regions, each of diameter less than 1, then the number of signed summations that lie in this R1 union R2 union Rk is at most the sum of the k largest binomial coefficients from n choose I of the form n choose I. So that is n choose n minus k plus 1 by 2, n choose 2 n choose n plus k minus 1 by 2. Yeah, n choose n plus 1 k. So the sum of all those k largest binomial coefficients from this series. That is what Bateman showed. Now, for k is equals to 1, if you think about it, if there is only one region which Arthos was trying to conjecture about, if there had been only one region which was our concerned region, then the binomial term would be the one largest coefficient from there, and the one largest coefficient from this is n choose n over 2. right? The middle coefficient, binomial coefficient that you get. That is what proves the Erzhoz's conjecture. So we'll show this Clayton's theorem, the proof of this. The actual proof of this is a bit advanced, so I would like to hand wave some things. But yeah, the proof has some very neat and clean ideas which are good enough for everyone in this audience. So the first idea is to remove the last sign that is there. That is, we try to induct. We will try to induct the thing. So we will compare using this n sign summations using n minus 1 signs. We'll remove one sign and then like try to look at it, and then we'll try to induct it back to n. So that's how induction works actually. So this is what we'll do. Now, now after that, we'll translate that remaining vector space of n minus, sorry, not the vector space, the remaining summation of the vector of n minus 1 to a different region and then some sort of thing. And then we'll use a separating wall. A separating wall is nothing but a plane. So think of it as a plane that is parallel, that is perpendicular to a given vector. Right, a separating wall. That is what it is. Someone is trying. So the proof idea is an induction, and the heart of it is a geometric separation picture, right? So moving on to the proof. Now, if you know the binomial coefficients satisfy this recurrence relation, this beautiful recurrence relation. So a bit digression from the topic of today. So if you know, Ardash was a very curious mathematician. So when he was in undergrad or something, he proved a theorem. I don't remember exactly which one, but yeah, he proved a theorem which was about 30 pages or long at that time. The least known, sorry, the most elegant known proof was 30 pages long. So he showed that in, I guess, 4 to 5 pages or something. So he was very fascinated with the binomial coefficients and the recurrence relation of this binomial coefficients and doing sort of things like that. So do give it a read. I don't know exactly which problem, like I don't remember right now which problem it was exactly, but yeah, you can give it a read. Like he was very keen of mathematics that was available to all. Like he gave proofs that everyone can read, like literally everyone can read, if he has a bit background in mathematics, a small bit background. So yeah, coming back to the top. So the binomial coefficient satisfies this relation. That is, n choose I is equals to n minus 1 choose I plus n minus 1 choose I minus 1. So the k largest indices, if you think about it, would be starting from n minus k plus 1 over 2 to n plus k minus 1 over 2. If you can think about it. So these R2s, if I define R to be n minus k plus 1 over 2 and S to be n plus k minus 1 over 2, then R2s will give me the k largest indices that are there. Right. Now, what Clayton told us was that the summation of this from R to S would be the maximum that I can get in that union region, that is unified region that I call as R1 union R2 union R3 dot union RK. In that unified region, I will get the maximum I can get is the summation R2S of n choose I. So what does this, wait, again it is black, I think. Okay, yeah, it came back. So if you think about it, this n minus 1 choose I, what I did is for this term right here, this second term that is there, I took this indices and then I took a minus sign of it. That is, can you tell about the open ball again? Okay. So coming back to the open ball, as someone asked. So open ball is something, wait, let me just write it down again. So, and wait, where was the open ball? Did I mention open ball in earlier? Okay, yeah, here. So the open ball is something like this. So you choose a point first of all, say X, you choose a point X, and then you want to calculate an open ball about this region. So we defined something as a length of a vector, right? If who was the one to ask the question? Yeah, Anika, Ankon, like, do you remember the length vector that norm vector that we defined for
Yeah, yeah.
the vectors? Yeah. So you take the distance from this point X to this point Y, and then you take it to be less than or equal to 1, this length. So if you think about it in the real number line space, it would be something like this. Okay, wait. Uh, define a point X, and then you take a +1 here and a +1 here. And this intervals do not contain the endpoints. That is, you don't contain x minus 1 and an x plus 1 because of the strictly lesser than sign. So this is what it is in a real line. And if you can think of it as in RD, that is in d-dimensional vector space. So it would look something in R2, it would be a ball. If you think about it, a circle of radius 1. In R3, it would be a sphere of radius 1. And in general, it would be in RD, that is there, that is real vector space of d dimensions. It would be a d-dimensional sphere in general. So that is the open ball of radius 1. Is it clear now? Good.
Yes, sir.
Okay. Okay. So yeah, where were we? Yeah, right here. So there's a bit of manipulation in this part of the thing that is there. So n choose I summation goes from r minus 1 to s, not from r to s, because I shifted this term of r to here, right? So that is how you can get about it. And then this would be the, as I shift the index from I minus 1 to I will shift the summation indexing running from r minus 1 to s minus 1, right? And then as I move this I equal to r term from here to there, so it would again club back, and then it runs from r to s minus 1, and this runs from r minus 1 to s. Right. Okay, any doubts here up to here? Anyone? Okay. So now what we said is we will separate a vector, the last term that is there, that is an. We'll separate this term out and we'll try to analyze this t, the summation from I equal to 1 to n minus 1. Right, we'll try to analyze what this is. So what happens to the target regions? So the target region is something, as you know, that it is inside inside some RL, right? This vector, that is t minus a1. If epsilon I is minus 1, then t minus an is in some RL, and then if epsilon n is plus 1, yeah, will the PPTs? Okay, yeah, the PPTs will be shared after the lectures. Yeah. So the epsilon n, if the epsilon n is plus 1, then it is a t plus an will be in the region, in some region RL. Right? It should be in some region RL. Otherwise, we will be finding something that is not in accordance to our problem. We'll always need to find something that is inside some RL. So then RL plus 1 plus an, that will be the region where t lies. And if epsilon n is minus 1, and if epsilon n is plus 1, then RL minus an is the region where the summation t lies. Right. I think this should be clear. This is a basic algebraic manipulation that I did. So a region plus a vector, what does this mean is you translate the vector about that vector space about that region using that vector, by that vector. So every vectors of this region is a vector from RL plus the vector from plus the vector an, right? And the region determined by this is the vector, some vector in RL, let's say v minus n. The vectors of this form v minus n and the v plus n. I think this should be clear. Okay, moving on. So the geometric claim, the key geometric claim that is there, that is among these regions R1 minus an to Rk minus an, at least one of them, say Rj minus an, some index j, for some index j, it is disjoint from all of these indices. That is R1 plus an, R2 plus an, and Rk plus an, all of these indices. So this will create, if this is a disjoint split that is there, that is Rj minus an is disjoint from each one of them, then I can take this Rj minus an to be in this set that is there, R1 plus A1, R2 plus A2, and R2 plus an, and then Rk plus 2, Rk plus an. And I can add the region Rj minus an, and that will not affect any of this other region that is there, that is R1 minus an, R2 minus an, Rk minus an. It will not affect those regions. So this creates the exact k plus 1 and k minus 1 split that is required. So if you remember, the k plus 1 and k minus 1 comes from here, right? This terms right here contain k plus 1 and k minus 1 terms, if you think about it. Right. Okay. Now, think of it as a this geometric figure that is given right here is something that you will understand a bit later after I introduce you to the real manipulations from here. So how do you read this picture is you have this wall. I said that you will get a wall that is there that will separate these regions, right? So this wall is perpendicular to, you take a wall that is perpendicular to AN, and then you translate region AN, Rj plus AN just touches the wall at some point, let's say y plus n, and Rj minus n is forced to be in the other, on the other side. So I will explain this in a bit while. Yeah, so this picture here. So coming back to the mathematical part of that. So this notation that is there, this is a inner product notation, an comma j. That is, you can think of it as a dot product thing. It satisfies all the properties of a dot product. So take the wall that is H to be all those vectors that have some c or some constant value for the dot product, a fixed constant value. Fix a constant c and then take the wall to be all those vectors that have the dot product of c. Now, a very interesting thing would be to show that this will be perpendicular to this wall, that is this plane that you created. The wall is a very vague term. The plane that you created, that is H, is perpendicular to AN. So to show that, it would require a bit of exercise. I would let you to do the exercise for that. But now, for now, suppose that it touches Rj plus An at some point y plus An. So in rigorous terms, this means that the closure of this region Rj plus An contains a point y plus An that is in that wall, that is in that H, right? Or in a very vague term, this is something like it touches that point at y plus n, so y plus n should satisfy this relation that is there. So an dot product with y plus an is basically c, and if for some x that is in Rj, and then if x is in Rj, then x minus an should be in Rj minus an, where on the wrong side. So the wrong side here means this part right here. So if it is Rj minus n, if it were in the other side of that, right, and from here to here, if it had been on the same side of this wall, then what would happen is I could define this side of the region to be the dot product that is greater than or equal to C, because this part is the point where it is equal to C, the dot product. This part is the point where it is less than or equal to C. And I can define this part of the region to be greater than or equal to C, the dot product of that, or the inner product in mathematical terms. Yeah. So if it were in the wrong side, then it would have been that there exists some point x in Rj, so that x minus an is an Rj minus a, and the dot product of this an and x minus an was greater than or equal to C. Now you can separate these terms if you know a bit of vector calculus or something. That is, you can break this dot products into two different terms. That is, this one to an dot product with y plus the norm of the vector an squared, and then this one to be an dot product with x minus the norm of an squared. A bit of algebraic manipulations and you would arrive at this quantity. Now combining this, you would arrive at this quantity, that is an with the dot product of x minus y is greater than or equal to 2 times the modulo norm vector of an squared. Now ans that were there, that was greater than 1. So as ans were greater than 1, you get that this quantity that is there, x minus y, is actually greater than or equal to 1, equal to 2, which contradicts the diameter condition if you think about it. As x and y are 2 points in Rj, and Rj has a diameter of length at most 2, which was a given condition if you remember. Wait a minute. Yeah, so the each of these diameters are at most 2 if you think about it. So that violates this condition, and hence we arrive at the point that no point of a Rj minus an will be on the wrong side. That is, Rj minus an is on a different is disjoint from all of these sets. This point Rj minus an, this region is disjoint from all these regions that are there. So that is what we had proved. Now this is it. Now if now from this you can get that you choose that particular j, and then you take this k minus 1 regions, that is r1 plus an, r2 plus an, rk up to rk plus an, comma rj minus n. You just add this region rj minus n to here, and that will give me nothing but a k plus 1 region. And the induction gives us that this many regions that are there will have a binomial term of the summations of k plus 1 binomial term, that is r minus 1 to s of this. This is my first k minus 1, and the second term of the binomial comes from this induction, that is the remaining k minus 1 regions, that is all those regions rl minus an, where l is not equal to j. So induction hypothesis gives me that at most summation from r to s minus 1, n minus 1 choose I, this many number of vectors will lie in that region. Is it clear? I went a bit too fast, but anyone with any doubts or anything, any questions? Yeah, you can speak. I think it's been a while. Okay, okay. And I think there are no doubts right now. So these are the exact two terms that are in the recursion, the Pascal's recursion or the binomial recursion that you get. So adding these two bounds and you get our original value. That is actually, this is the exact summation that you get from the sum of the k largest binomial terms. So the Clateman's theorem follows. Now the big picture of this is that Littlewood and Offord asks how many signed summations can concentrate within that ball of radius 1, right? If you had forgotten, our original question started with if I had taken complex numbers, what would have happened? Here's the original question that was there. That is, if I had started with complex numbers, each of them having greater than or equal to 1 modulo, then how many of these signed operations will lie in a circle of radius 1? So this has been answered because our C2 can be viewed as a R2 vector space. So then if you can view it as an R2 vector space, then you can obviously do all those things that you had done with R2. This thing would be there. So coming back again. So Littlewood and Offord asked how many of these signed sums can concentrate? And then Ardosh found the exact real line answer using Sperner's theorem. And then Clayton proved the multidimensional result by combining the induction with geometry and all these things that you saw right now. And then the crucial geometric step was separating this hyperplane. So in R2, it is called a plane. In R d dimensions, it is called a hyperplane. This wall that I said, separating the picture. And the final bound can be controlled by the largest layers of the Pascal's triangle. That is, the k largest terms of the Pascal's triangle are the binomial coefficient. So even if you start with very long arrows, you cannot send too many plus and minus signs into a small target, right? So if you want to read it further, these are the references that you can take. So the first reference is this one, by Littlewood. This is a paper where Littlewood and Offord discussed about this problem. Like this, they said about this problem actually originates from the polynomials. Like if you have been given a random polynomial whose coefficients are randomly generated, what would be the roots of those polynomials? So that is called as the random zeros of polynomials. That's a bit uh, higher in knowledge. Like you would require a lot number of prerequisites to understand that paper. But yeah, this one you can definitely understand or go through. The Littlewood and Offord's paper, work on random algebraic equations. Then there is a Paul Ardash's paper on a lemma of Littlewood and Offord, 1945. So this is the paper where he proved the real number line case. And then the Kleitman's paper on Littlewood and Offord's lemma, 1960s to 70s. I don't exactly remember the year. So in this one, he showed the d-dimensional case or the multi-dimensional case for this theorem or lemma. And there's another book that is called as Eigner and Ziegler, proofs from the book. So there's a chapter on there from named as on a little lemma of Littlewood and Offord. This book generally has a lot of interesting topics, interesting lemmas to see. A very clean and well-written book. You can read on this book also. So that's my time here. So I'll stop presenting, and if there are any questions, I will take the questions if possible. So anyone with any question that you have? Questions, anyone? All right. So that's it for today. Thank you, everyone. And okay, you have your next session from 1 p.m., right?
Yes, sir.
Yes. So thank you. Thank you, everyone. We'll see you later.